Hello and welcome back to this series of videos as we journey from the very simple primes to the foothills of the Riemann hypothesis. Today is another appendix style video where we explain some of the tools we've used on our main journey. We didn't want to bog down the main journey with lots and lots of side detail, so we've separated them off into appendices, as it were. And today we're going to look again at infinite products because we looked at them before, but we didn't go deep enough into them, and we've had to use some results, and we want to explain where they've come from. So this is a second look at them, and hopefully this one is more satisfactory. I'm pleased because it really explained a few things for me. Right, so let's start at the beginning. At school, we often learn about infinite series, and we kind of become very familiar with them, and we learn lots of techniques to work out, how they converge or diverge, and that's something you'll find, lots of information about in all the textbooks and courses. But for some reason, infinite products aren't really mentioned as much, and it can be quite hard to find information. I certainly found it quite difficult. So today's video is almost like a summary of some of the things that I've had to find out for myself. So let's look at a very trivial example. This first one here, 2 times 3 times 4 times 5 times 6 times 7 and so on. It's easy to say that diverges, and intuitively we can say that because each factor increases the size of the product. So 3 grows a product, times 4 grows it even more, times 5 grows it. So you can see that an infinite number of them will kind of grow it infinitely. So that's not too difficult a leap to make. Another really fundamental idea in multiplication is that if we multiply by 0, or if there is a product with a 0 factor, the whole thing must be 0. And we want to hold on to that. So if we take the same thing, but actually put 0 in, we will say that's 0. That's kind of a foundational fact. We don't want to be in a position where if we invent a theory of infinite products, multiplying by 0 doesn't give 0. That would be kind of inconsistent in a way. So another more interesting example is this one. The others were a bit too kind of uncontroversial. This one is more interesting and it's worth thinking about. So half is a fraction, times a third, a smaller fraction, another fraction, another fraction. What do you think happens to this product as the number of these terms keeps growing, extending? Well, each one is reducing the size of the product, because this is making it a third of what we had, a quarter, a fifth. So each one is making it smaller and smaller. So it's easy to argue that an infinite number of reductions, shrinkings, make the product tend to 0. That's not too controversial, but did need a little bit of thought. But the interesting thing, the important point here is we've now found 2 ways that an infinite product can be 0. And this doesn't apply for normal non-infinite, as in finite products. With finite products, the only way they're 0 is if one of the factors is 0. With infinite products, either a factor is 0, like this one here, or the factors keep shrinking their partial product, as it were. So we have 2 ways of making a product 0, so we have to keep that in mind. That's the first difference, I guess, or a new idea that we perhaps didn't expect. So let's go back to this, the idea of a definition, and it's similar to infinite series, where it's defined, an infinite product is defined as the limit of the partial products, as in the upper, the n goes to infinity, where n is the index of the terms. It's very similar to, it's almost parallel to infinite series. And you might say, well, we don't often use this a lot, but actually it can be useful, and we'll see why. And we'll also add something to the definition, which we'll come back to later to see why it's the case. We'll say an infinite product converges if the limit of the partial products is a finite value and is non-zero. Now this is the surprising bit. because that doesn't happen with infinite sums. But with infinite products, we're going to say it has to be non-zero, and if it is 0, then we have to say that it doesn't converge. That's the convention, and we'll see why that's become the convention. So let's look at some examples just to practice this idea of partial products. So let's look at this one. This is the form for the terms, 1 plus 1 over n. And if we have an infinite product of them, does that converge? Well, we can just take a look at that and say that each term is going to be larger than 1, even though it'll be larger than 1 by an increasingly smaller amount. Each term will be larger than 1, and that means the effect of multiplying numbers that are larger than 1 is to grow the size of the partial product. So we expect this to keep growing, and we can then guess that it diverges to infinity. That's the intuitive guess. But let's work it out properly. So we can actually write this out. We can rearrange that as n plus 1 over n. So the first term will be 2 over 1. Then we've got 3 over 2, 4 over 3, and so on, all the way up to n plus 1 over n. Now, actually we notice that we can cancel in a systematic way those 2, those 3, those 4s, those 5s, and so on, which leaves n plus 1 as the product when we have a partial product up to n. So we can see straight away that as n goes to infinity, it diverges. So instead of doing it intuitively and hand waving, we've actually shown it properly through the idea of partial products. So that's not a surprise, but it shows the technique. Let's look at another one. This one has a minus now instead of a plus, so each term is a bit less than 1, and our intuition is that terms that are less than 1 multiplied together keep shrinking the partial product. So maybe the value of this goes towards 0. Now notice we start at n equals 2, because if we start at n equals 1, it's 1 minus 1, which is 0, and that just makes the whole thing 0, and that's not interesting. So let's work it out properly. And again we can write out the terms and spot a pattern. So this now becomes n minus 1 over n. So it's 1 over 2, 2 over 3, 3 over 4, and so on. And then we can cross out in a systematic way, leaving 1 over n. So as n goes to infinity, the value, the limit, approaches 0. So we say the product goes to 0, and in fact diverges to 0. That's the expression we use, because we said convergence has to be non-zero. We'll see why. So again, looking back at infinite series, we know that with a series, a sum, the terms, for the series to converge, the magnitude of the terms has to approach 0. With an infinite product, you can probably kind of work out for yourself that the terms need to approach 1, because if they didn't, if the terms approached more than 1, if they remained more than 1, the product would ever get larger. If they remained less than 1, the product would get smaller. If they were negative, or if there were some negative terms, then the partial product oscillates, because multiplying by a negative number flips it from, say, plus 5 to minus 5, or plus 0.5 to minus 0.5. So that oscillation is not convergence. So the only way to avoid that is if those terms approach 1. So that's a useful kind of intuition to have, and it's a requirement as well. The other thing to say, and we kind of touched on this with one of the examples before, is we saw that a single factor of 0 collapses the entire product to 0, and that can be boring. That's not interesting. So if a product has a finite number of zeros, factors which have 0 value, then we can remove them and have a different product that might be interesting. So here's an example that we looked at before, but this is using n squared. So 1 minus 1 over n squared, if we have a infinite product over that, starting at n is 1, in the first case n is 1, 1 minus 1 is 0, so the whole thing is 0. That's not interesting. But if we ignore the first one and have a different product, which is just the first one with the first term removed, starting at 2, then that's a more interesting infinite product. It tends to a half. We won't work that out here, but this is just to illustrate the idea that if there are a finite number of zero-valued factors, we can remove them and study the remaining products as a different product. So let's think about some convergence criteria. Let's start easy with a simple case of real numbers, and then later we'll look at complex numbers. So because we've seen the terms have to approach 1, it's useful to be able to write the terms as 1 plus an. That just kind of, it makes sense, but it also is helpful as well for what we're going to do. But you can think of it as the an's then have to go to 0 because the factors have to go towards 1. So if we turn the product into a sum by taking logarithms, that's a kind of common technique. We have log p is the log of the product 1 plus an, and remember the log of a product is the sum of those logs. Now we can use an inequality, 1 plus x is less than e to the x. You can visualize that, you can graph it, or you can verify it by writing out the kind of the series expansion for e to the x. You'll see that 1 plus x is always less than e to the x. That's useful because this is 1 plus x. So the log of e to the x is just x, which means we're left with a much simpler sum. Let's do that. So we've got the sum of log of 1 plus a to the n, and we've said that 1 plus a to the n is less than or equal to e to the an. So that means that is less than the sum of the log of e to the an, and log of e to the something is just sum an. That's where that's come from. So that's a nice useful inequality straight away without too much work. What this tells us is that if this converges, or well, if that is bounded, doesn't grow to infinity, because this is less than, the log of p is less than that, that means the product must be bounded as well. Let's say that again. If that sum is bounded, and because it's more than log p, that means p must be bounded. But if we add an additional constraint to say that if an are always more than 0, we're thinking about real numbers here, not complex yet, that means this sum can only grow monotonically. That means it doesn't oscillate, it doesn't go up and down, there's no negative values, it can only ever grow and not go down. So that means we can talk about convergence. That means if this converges, if an is more than 0, then this converges if it's bounded. Then p is also convergent as well. The product is convergent, so that's useful. If we could have a result that went the other way, that said if p is convergent, then the sum here is convergent. If we could do that, then we'd have a really nice nice kind of result. Let's see if we can do that. So if we think about this product and expand it out, we know that we'll have 1 plus multiples of combinations of various terms. Let's write it out pen and paper. So if we've got 1 plus a to the n, and that's the product, we'll have 1 times 1 times 1 times 1, plus we'll have all the an's like a1 plus a2 plus a3, plus we'll have combinations like a1, a2, plus other ones like a1, a3, a5, and so on. If we just pick these, we can say that 1 plus the sum of a to the n is less than or equal to that product, because that's the difference is those extra terms, 1 plus a to the n. All we've done is just taken some of the terms from the product expansion, expanding out the brackets. That's what we've done here. So we said 1 plus the sum of all those terms and remember they're all positive now, is less than or equal to the proper full expanding out the brackets. So that means if the product converges, then so must the sum, because it's the other direction now. So we've got it in both directions, and that's the first result, and that's why there's a bidirectional implication here. If the sum converges, then the product, this product, converges, or if the product converges, this sum converges, as long as an is more than 0. The terms, the ans are more than 0. So we can use this to say 1 plus 1 over n, that product, diverges, because we know the harmonic series diverges. We can say this thing converges because the 1 over n squared, the Basel problem, converges. That's a nice way of looking at these products and spotting whether they converge or diverge. That's really, really handy. So that's the first convergence criterion that we found, but it's only for real values of an more than 0. Eventually we want to come up with a result for complex an, so we'll get there. Now, actually, you might say, well, wouldn't it be useful to have something where an is not more than 0? If you think about it, an can't be too negative, because then the factors are larger in the negative direction than 1. So let's write that out. So if we said 1 minus an, that's the product. So for this thing to converge, this product, we can see straight away that those ans can't be too large. So an, if it's between 0 and 1, then we can see that that thing converges. If it gets larger than that, then the brackets, the factors, have a larger magnitude than 1, and we can see that diverges. So we won't do the algebra here because it's not that interesting, but you can use a different inequality and we'll end up with a very similar result that says that if the sum converges, then this product converges as long as an is between 0 and 1, and the same in the other direction. So that's a useful second criterion. It's similar logic to the previous one. And then we can say something like this product, this infinite product, diverges because the harmonic series diverges. Now let's talk about this idea of divergence to 0 again. Where did it come from? So the logarithmic view of those infinite products, remember when we apply the logarithm to turn the product into a sum, that's useful because sums can be easier to work with, but it has an interesting side effect, because if the partial products tend to 0, then the logarithm tends to minus infinity. So if the partial products tend to 0, then we say it diverges to 0, because in the log view, the logarithm will tend to minus infinity. That's where the root of this is. We will come back to this. So we've previously had convergence criteria for real values, and it would be good to have convergence criteria for complex numbers, complex an. So we just need an intermediate result first, and then we'll get the final criterion for that. So for complex an, we can actually reuse the first criterion, because the first criterion was about an more than 0, and if we take the magnitude of a complex number, it's always going to be more than 0 as long as the complex number isn't 0. That's kind of a straightforward observation. So we can say the magnitude, the sum of the magnitudes of a of the an where they're complex, as long as they're not 0, if that converges, then the product here converges, so it's 1 plus the absolute values. I haven't put a box around that because it's not that useful, but it's a kind of an intermediate step. This isn't particularly anything new. All it's saying is these terms are more than 0, and that's what happens when you take the absolute value. as long as they're not 0 themselves. So there's nothing magic there, just a little step. So we're interested in, and just to clarify what we said, we're interested in the product of 1 plus an for complex n, not just where there's the absolute value, the magnitude taken of that complex number, but this will be useful in getting us there. So let's define two partial products, Pn, where we're using the complex value, complex an, and Qn, where we're using the absolute value. And we're going to compare them, and we're going to say that an is not -1, otherwise that would be 0. So we want to avoid the 0 valued factors. Now we're going to do a little bit of algebra. We're going to say for n which is greater than m, which is greater than 1, we want to compare the difference of the partial products. So Pn minus Pm, the magnitude of that, with Qn minus Qm, the magnitude of that. You might have spotted, if you already know, that this is the Cauchy approach to working out whether a sequence converges or not. But if you don't know, that's fine. We're just going to follow the logic. So we're going to say Pn minus Pm, the magnitude of that is, we can kind of rewrite that expression as Pn over Pm minus 1. And this thing is useful, that's why we've done it, because that's the product of 1 plus a to the n from m plus 1 to n. Because these are partial products, remember, so it's dividing by the first m, but leaving the factors from m plus 1 to n. So that's that. Now we recognize that Pm is going to be less than or equal to Qm, because Qm was made of the absolute values, which are always going to be, this will always be less than or equal to this one. So that's less than or equal to Qm, and the same happens here where we replace an with the magnitude. It will be less than or equal to, and then we can recast this as Qn over Qm. So we come to the conclusion that Pn minus Pm, magnitude of that, is less than or equal to Qn minus Qm. Now this might actually have been intuitively obvious to you, but it might not. So this actually works it out. If the Pn minus Pm, if this one here, Qn minus Qn, this is the one with the absolute value, if that's always less than the magnitude of that difference, if that's always less than an epsilon, no matter how small that is, then because that's less than or equal to the analogous Pn minus Pm, the magnitude of, will also be less than that small epsilon. What that's saying is that if the sequence Qn converges, then so does the sequence Pn. This is a Cauchy criterion for convergence. It's fairly standard, it's worth looking up. If there's a lot of demand, I can do a video on it, but it's fairly standardly taught. So this is saying that if this one converges, then so does this one. We just showed it. It might actually be obvious to you, because we often say if something converges absolutely, then it also converges conditionally or normally. But we've just shown that rigorously. So if Qn converges, so does Pn. So this is the final logic step. If the series of absolute values of an, where it could be complex, converges, then the product of this form with an magnitude converges. Now we've just shown, so that was the first result here, which was just essentially the very first one we had. That's just that up to there. And then we're saying because this converges, the Qn, then so does the Pn, the product with just the complex numbers. So it's worth writing that out, or kind of pressing replay on this YouTube video just to understand that logic. And that means we've got a convergence criteria for when A is complex, but only in one direction. We haven't shown it in the other direction. So if the sum of the absolute values of those complex numbers converges, then that product with an not having magnitudes applied, just the an, converges, as long as an is not -1. That's useful. So we finally got there. So just to reiterate, that's one way, whereas the other criteria were two-way. So here's a summary for real ANs and real AN and then complex. So if the sum converges, so does a product there. We've got a -1 here, which has a different range of validity, and then the very interesting one with the complex AN. So if the magnitude of those AN converges, or the sum, then that product does as well. So that's a summary of what we found. So often we'll kind of apply these convergence criteria, and they might tell us that something converges or doesn't converge. And we said as part of the definition earlier that if a infinite product tends to 0, we don't say it converges, we say it diverges to 0. So the question is, if those convergence criteria say that a product does converge, how do we reassure ourselves that that's a non-zero value? And that's a question that I really struggled with, and it took me a while to ask around and find the answer. It seemed like a bit of a gap in the logic that a lot of the textbooks just kind of ignored or skipped over. So I did, if I don't mind saying so, a fair bit of work to try and get the answer, and it might be obvious to you, but it wasn't to me. So let's explain why. We know that those AN must tend to 0, so that the factors tend to 1. That means that those magnitudes of AN will be less than any chosen value, let's say half, because only a finite number of those AN will have magnitudes more than a half. Could have chosen 1, could have chosen 10, could have chosen 0.01, but half is going to be useful to us. I hope that makes sense, because ANs are getting smaller in magnitude. That means all of them will be less than half, except a finite number. I hope that's clear. Going to use that inequality again. 1 plus x is less than or equal to e to the x. So we're going to say this product with the magnitude of the AN there, this is less than e to the sum of AN, using this inequality. Right, and we can see already straight away that that's more than 1, more than or equal to 1, because these only consist of positive values, 1 plus a positive. Lots of these multiply together. The smallest it could ever be is 1. Great. So if the sum converges, then the product converges and is non-zero. It's going to be more than or equal to 1. That's the first few steps. That's useful. We need to show it in the other direction. We're going to use another inequality. 1 minus x is more than or equal to e to the minus 2x. Again, you can visualize this by graphing it, or you could work it out if you wanted to. You do that with gradients to show that this is a convex function, so it's always going to be less than. This is always going to be more than that. In this range, it's not true for any generally. So we're going to use this to say that product again. Now this is an absolute value, so it's positive. So 1 minus a small positive. If I multiply all these together, it's going to be no more than 1, because it's 1 minus a little bit. So the most it could be is 1. But according to this inequality, it's going to be more than or equal to e to the minus 2, what the sum of those ANs. Now e to the power of something is always more than 0. Remember, this is not complex now, this is magnitude. So e to the minus e to the plus even, e to the anything real is more than 0. So that product is more than 0. If that sum converges, then the product converges and is non-zero. So let's summarize what we've said there. We've said, a recap, we've said if the sum converges, then this product with a plus there converges. The second result is if the sum converges, that product with a minus converges and is non-zero. So those are two cases we've come up with. And now we're going to use an inequality which, if written this way, is obvious. 1 plus or minus an is more than 1 minus that magnitude of an, and it's less than 1 plus the magnitude. So this grows it, this shrinks it, and this is, it could grow or shrink. That's kind of a statement of the obvious, really. It just looks complicated. But when we recast it as those products, we can say a minus 1 minus that magnitude and 1 plus that magnitude, and then in the middle we've got the plus or minus. What that's telling us is that if that sum converges, then the product in both directions, plus or minus there, is non-zero, because we've showed that in both cases is non-zero, because its value is between so let's restate that. This product has a complex number in. We're not taking the magnitude here, but we know it's going to be less than this quantity and more than this quantity, and we've just shown in the last two slides that this is non-zero if it converges, and this is non-zero. So this is going to be between two non-zero values. That's why we can say this converges, then the product converges is non-zero. Phew, that took me a while to kind of establish and prove to myself, and I hope that's useful. And it's useful because we can then say, if those convergence criteria tell us that something converges, we know the product converges to a non-zero value. That's the important thing. So let's apply this as we did on our main journey with the Riemann Zeta function. So we know the Riemann Zeta function can be written as this series, defined for sigma more than 1, where sigma is the real part of S. And we also know that it can be written as an infinite product over primes. So the question is, can this be 0? Does it converge in this region? And when we say converge, remember the infinite product must be non-zero. So the first thing we can spot is there's no factor that's 0. Remember, p are primes, and if a factor is going to be 0, that would require this ps to be 0, and that's not possible. We can see that by writing p to the s magnitude is e to the s ln p, and that's the real part, e to the sigma ln p, and that's always more than 0. E to the something real is more than 0, so that pts can't be 0, and therefore none of those individual factors can be 0. So it's not going to be 0 in the normal method of multiplying by 0, but we need to check that it doesn't diverge to 0, and that's where the convergence criteria help. So for the moment we're going to consider 1 over the zeta function, just to get rid of that minus 1. That's usually up there. So this looks more like the form we were working with. So 1 minus 1 over p to the s. And the convergence criteria, we just need to check that the magnitude of 1 over p to the s converges. That's all we need to do. So the sum of 1 over p to the s is, the magnitude there is p to the sigma, which is less than 1 over n to the sigma, and the only reason that's true is there's more n than p, so the primes are a subset of the integers, that's why it's less than. I know it says less than or equal to, but it's less than. So this converges for sigma more than 1, that means this does as well, because this is larger quantity than that quantity. So that means 1 over sigma converges to a non-zero value, and therefore if 1 over sigma converges to a non-zero value, then sigma inverted converges to a non-zero value, and therefore the Riemann Zeta function has no zeros in the region sigma more than 1. And that's our conclusion. Lovely. Well, I hope that you found that useful as a recap and a deeper look at infinite products and the application of some of those convergence criteria to the Riemann Zeta function. Fantastic. I hope you enjoyed that, and we'll see you next time. Bye.